Alkyne synthesis. Synthesis problems are an important part of organic chemistry. They essentially teach a certain type of logic to them. So, in this problem, what's asking is to make this molecule, but the materials that you have to use either contain 3 carbons or less, and any carbon-containing molecule must be non-ionic. So what we have here is 1, 2, 3, 4, 5, 6, 7. We have a 7-carbon long chain, and we need to make it. Well, the way we make alkynes is through an SN2 reaction, where the nucleophile happens to be a deprotonated alkyne. So the bond that we always make is a bond next to an alkyne, next to the triple bond. So we can make either the bond between carbons 3 and 4, or the carbons between 5 and 6. Let's go ahead and make this bond here. So if we do that, we split it up like so. We have carbons 1, 2, 3. Here we have carbons 4, 5, 6, and 7. Now, this carbon on the left, the sp3 side of that split gets the leaving group because this reaction is an SN2 reaction. The sp side, on the other hand, gets a sodium because that is a nucleophile. Now, this molecule here has 3 carbons, so it obeys the first rule of having 3 carbons or less, and also this is not an ionic compound. So this molecule is good to go. We can use it. This molecule, on the other hand, has 4 carbons. So we have to make it. We cannot stop. To keep going. And the way we make a deprotonated alkyne is to simply start with a terminal alkyne, like so, and add a base to deprotonate it. The base that you want to use is NaNH2. And basically it's an acid-base reaction. This deprotonates that and gives us our terminal alkyne. This molecule contains 4 carbons, so he doesn't obey the rules yet. This NaNH2, well, it's an ionic compound, but it doesn't contain any carbon, so we're okay to use that. So I'll have to make him. Well, he is essentially an alkyne. So carbons 4, 5, 6, and 7. Here we can just make the 5-6 bond. The 5 side gets a sodium because that acts as a nucleophile. And the 6 gets a bromine. This has 2 carbons, so obeys the first criteria, and it also is non-ionic. This molecule has 2 carbons, but it's ionic because there's a sodium in there, so we have to make him. Make him by using sodium amide and add that to acetylene. This molecule, acetylene, has 2 carbons, non-ionic, so check, we can start that. And here is the synthesis, and all the materials now that you start with obey this rule. Now, we could have done it this way. We could have also have made this molecule instead of splitting at the 3-4 bond, we could have split it at the 5-6 bond. So get this plus ethyl bromide. This, of course, follows the rules. This doesn't, so we have to make him. Can't stop. Make him by adding NaNH2 to a terminal alkyne. This has 1, 2, 3, 4, 5 carbons. So we can't stop you there because 5 is not less than 3. So again, to make him, and we can make the 3,4 bond. This 3-carbon piece follows the rules. We can stop there. This is ionic, so again, we have to make him. So we can't stop on this side. There. This is now, again, 2 carbons, non-ionic, we can stop. So either the green pathway or the red pathway will give us the same product. Both of them are equal. Let's talk about this molecule down below. This one, on the other hand, like the first one, is actually symmetrical. We have 2 propyl groups on both sides, the alkyne. We can do it a systematic way of doing one, then the other, just like what we did above, or what we could do is actually put both of them on at the same time. The way we do that is we split them both. We have a sodium on one side and a sodium on the other side, like so. In this molecule, we can either say we use 2 equivalents of it, so for every 1 molecule of the sodium compound, we have 2 of these, or we can also use the word excess. Either one to give us that. This molecule, on the other hand, is definitely ionic, so we need to make him, and so we can make him by using an excess of NaNH2 plus acetylene. Or we could also use the word 2 equivalents of NaNH2 because we need 2 of these to give you that. React with that. Okay, so this is a viable option for this. Okay. This can be used for the bottom case only because this alkyne is symmetrical. The top alkyne is non-symmetrical. You have a propyl group on one side, an ethyl group on the other side, so you cannot use this matter. Reason being, is if you tried. So start with acetylene, and you add your excess NaNH2 to that. You can get your disodium species. And if you add this ethyl bromide to give you the one side, and propyl bromide to give you the other side, you would indeed get the product that you want. But you would also get two products that you don't want, where you give them with both propyls or both ethyls. So instead of getting the product that you want as the major product, you get a mixture of all of these products, meaning this is a case. This is bad. The synthesis that you want to make is the one that gives you your target product as the major product. Okay. In synthesis problems, there are a lot of correct answers, but there will always be more incorrect answers.